Here we develop the general solution of the integrating factor from a first order linear Diffie-Q. This is the standard format of the first order linear Diffie-Q. The coefficient of y prime is 1. If it isn't 1, we need to multiply or divide through by something to get the coefficient to be 1. Q of x in context of circuit analysis could be a voltage forcing function. Like with an RL circuit, we're doing a source-free circuit. The analysis starts when the voltage source is 0. So 0 is a reasonable value, a valid value for Q of x. Now that we have this, we can use a regular separation by parts and get this equation into a form that we are able to integrate. And we're still working on a general solution, so we're still separating the parts and integrating. Here the differentials are separated. We can integrate this. We have a natural log of y, and then the implicit integration on the right side. The next trick here, natural log of c, is a constant. Natural log of 5 is just a number. Natural log of c is still a constant, and this gives us a way to write natural log of y minus natural log of c, so we can write the natural log of y over c, equivalent form of that. The right side is still implicit. We can raise both sides to the exponential, and we end up with this right here. This is at the bottom of page 1028, Tsiolkovsky Calculus, 5th edition. The next step, they take the derivative of the left-hand side expression. They don't offer any other explaining. That's what they do. When we take the derivative of this expression, it's going to be equal to this, so we make an equation out of it. And this is what we have at the top of page 1029. The equation has been factored slightly, and we see that we have the y prime plus p of xy, which from the original first order linear Diffie-Q is equal to qx. So qx is reintroduced. We see this by inspection. So we haven't really actually eliminated qx. This is still the original equation here. We were taking the differential of the left side expression, and it equaled this side, and now here we multiply through by dx differential. So still our left side, and the equation that looked a little messy now looks like this. This becomes our cheat once we see the generalized pattern. We can really only finish when we have an explicit first order linear Diffie-Q to work with from the beginning. What we see here is we have y times the integrating factor, and here we have qx times the integrating factor. And then we, of course, d differential on the left and dx differential on the right. So really, if we forget y prime and ignore p of x, and all we have left is y equal q of x, we can multiply both sides by the integrating factor. Y times the integrating factor equals q of x times the integrating factor. And that becomes the quickest cheat to use the pattern of the general solution, which is what we have here. So here's an explicit first order linear Diffie-Q. The coefficient of y prime is x, so we need to divide by 1 or multiply by 1 over x. So we get the coefficient is now 1. We see p of x is minus 4 over x. So here we have our integrating factor, with p of x is now the integrand, and we integrate this. Of course, 1 over x is going to give us a natural log of, and then e is going to cancel out the ln natural log, and the explicit integrating factor is x to the minus 4. We multiply y times x to the minus 4, and we multiply our, this is our new version q of x here, so we have q of x times the integrating factor. We reintroduce then the d and dx, so we can integrate, and if we perform this final integration, so working with the general solution of the integrating factor can be quick when we ignore y prime and ignore p of x and just use y equal q of x and multiply that by the integrating factor. So you can back up a few steps and multiply through by the whole thing, but the general solution comes down to something quick and fast. Y equal q of x multiplied by the integrating factor, what I did here. Yeah, I want to say too, all of this, I didn't make this up. Tsiolkovsky Calculus 5th edition didn't make it up either. All of this, this general solution was done back in the early 1700s. It's ancient mathematics